Hey everyone, so Chapter 9 covers running water and groundwater, and I'm going to split those up into two online lectures. First we'll cover running water. So the Earth really should be called, it's kind of a misnomer, should be called Oceanus because it's just covered by water. 70% of the surface of the Earth is the ocean. And most water on Earth is in the ocean, is ocean water, about 96.5%. The majority of the rest is freshwater. So this is the global freshwater is about 2.5%. And if you break that 2.5% down, in fact, most of it, of that freshwater is locked up in glaciers and ice sheets. About 30% of that is groundwater, and only 1.3% of that is surface freshwater. And if you take that surface freshwater and find out what it is, most of that superficial freshwater is snow and ice, snowpack, and like mountain ranges. About 20% lakes, and rivers only make up about 0.46% of that water. And that's all rivers. So the Amazon, Mississippi, Orinoco. Okay. And here's a breakdown of the rest of the superficial water: swamp, atmosphere, biological water. Ooh. So there's a hydrological cycle, and this is just how water moves through the different reservoirs. And there are a number of different processes that encompass that movement. Precipitation is rain or snow, so water condensing and falling down back onto the land surface. Then there's evaporation, so that's water moving from its liquid phase to the vapor phase and going back into the atmosphere. Infiltration is this right here, water soaking through the ground and becoming part of the groundwater reservoir. Runoff is water running off the surface in streams, gullies, and ultimately into rivers and into the ocean. And then transpiration is water used up by plants for their processes, and then it runs through their leaves and back into the atmosphere. Here's a global annual estimate of the amount of water that kind of travels through those various processes. So evaporation accounts for approximately 320,000 cubic kilometers is evaporated from the oceans on average every year globally. Then most of that falls down on the oceans through precipitation, but about 96,000 cubic kilometers falls as precipitation on land. Then there's runoff, 36,000 cubic kilometers, and then about 60,000 cubic kilometers of water evaporates or transpirates back into the atmosphere. Okay, so if we're talking about water that runs off the surface of land, we call that runoff. And when we have running water on the surface of land, we have to designate areas that contribute water to local streams, and we refer to those as drainage basins. And they essentially contribute water to larger river systems. Okay, so you can see that here it's outlined in darker green. This would be the drainage basin. And in between drainage basins, there are divides, and they're essentially just ridge areas or highland areas where if it rains on a divide, the water will kind of run off in two separate directions into two different drainage basins. By far the largest drainage basin is the Mississippi River drainage basin. So if it rains anywhere along these kind of subsets of the Mississippi drainage basin, that water will come out and dump into the Gulf of Mexico. So this is a pretty huge area. Okay, here it's outlined in green. So if it rains anywhere here in the Midwest, that water is ultimately going to run through the Mississippi. And then there are continental divides. That's this right here. And the continental divide, so if it rains on this divide, some of that water will be part of this drainage basin, and then the rest of the water will kind of move out westward. And here, a lot of the superficial waters don't make it out to the ocean. They'll either go to reservoirs or evaporate away. But the Continental Divide runs right through Yellowstone National Park. And on the east side of the drainage basin is the Appalachian Mountains, so that's a natural divide for this basin. So river systems drain much of the land area. There are exceptions in landscapes and really in polar regions and also in deserts. So there's a variety of different types of rivers that kind of carve through the landscape, and it really reflects the number of different environments that they're in. Climate has a huge effect on river systems, as well as human intervention and the way we alter rivers. But we can divide rivers up into 3 zones. The sediment production zone, where erosion is dominant, and this is typically the headwaters of the rivers or the beginnings of the rivers at higher elevations. Then the middle of the river is the sediment transportation zone, where deposition and erosion occur at the same time and roughly equal. And then at the end of a river, ultimately where sediment is deposited. So the sediment production zone is where sediment's derived. Okay, so this is kind of like a visual representation of this portion of the river up in the mountains with exposed bedrock. The water is kind of breaking through this rock and kind of creating sediment. Chemical and physical weathering and mass wasting are occurring. And the sediment is generated by kind of breaking that bedrock into smaller pieces, bank erosion, and even scouring the channel bed. So that means the water is kind of digging its way downward at the bottom of the channel, which is down here. The sediment transportation zone, this is where sediment is transported. Not too sure if this image is working. I don't know if you can see this, but there's the 2 rivers are kind of converging on each other. One is laden with a lot of sediment, and you can see it by its kind of brownish color over here. And then on this side is kind of a clearer river. So this portion of a river is full of sediment in suspension. Okay, and the middle part of the river, the sediment transportation zone, you're having a lot of deposition of sediment as well as erosion from the local area. And then ultimately, the ends of a river, when a river reaches a larger body of water, either a reservoir or most often the ocean, then most of its sediment load is deposited, and it creates huge features called deltas. So here's a nice way to visualize those 3 zones. Here are the headwaters. This is a zone of sediment production or erosion. Here is the zone of transportation. If you notice, the river kind of, its characteristic, its flow kind of changes, its direction of flow. It's more of a meandering style back and forth once it gets to lower elevations. And then here's a zone of deposition where you'll have the mouth of the river create some depositional features like a delta. So there are a number of different drainage patterns, and it varies by the terrain it kind of cuts through, the bedrock that's available. There are 4 most common drainage patterns. There's dendritic, which is pictured here. Okay, almost looking like nerves in your body. There's rectangular, radial, and trellis. Let's go to the next slide. I'll show you those pictures. So here's dendritic. This is the most common pattern, and it develops when the bedrock or surface materials are uniform. And what it looks like, it kind of looks like a tree without any leaves. And so here's like the main artery. The flow is in this direction. And then these are all the little smaller order streams kind of contributing to the main flow here. Then there's the rectangular or Minecraft type river, the rectangular pattern. And this forms in bedrock that's highly jointed. If you remember, jointed rocks kind of form these straight lines where it kind of expands open, and so the water will flow along those preferential pathways. Then there's a radial pattern. If you've got a major geographic feature like a volcano, then all of these rivers will kind of radiate away from the major feature. And then the trellis pattern, This pattern shows up when you have two different types of rock exposed at the surface, one that's easily weathered and one that's very weather resistant. And so what happens is the water kind of runs on the less resistant bed here, and then every once in a while we'll jump the more resistant bed in one spot, and then we call that a water gap. I'm sure maybe you've been on like a family vacation and off the side of the highway they're like, oh, the Delaware water gap, and you stop to go check it out. Typically you'll see like rapids or perhaps even a waterfall. All right, so there's different types of stream flow in rivers. This is the more turbulent kind, extreme whitewater rafting, woo, right? This is where you have high velocity water moving through a river, which is the most common type. And then there's this type of flow, which is called laminar flow. This is more appropriate for areas of low gradient, not too much elevation change. So Florida or like the Florida Everglades would be a great example of sheet flow or laminar flow type rivers. So the factors that determine the velocity or the stream flow of water through rivers is really most important is the gradient or slope. If you have a higher gradient, that means there's more gravitational energy pulling down on that water, so it's going to move faster, right? It's kind of like holding up an empty bottle of water, and if you, slightly tilt it, some water will come out, but if you tilt it up, kind of create a huge slope, then water will come pouring out faster. Other features, the channel itself, the river channel, its shape. If it's narrow, you'll have faster moving water. If it's larger, you'll have faster moving water because you have more discharge. Discharge is the volume of water flowing past a stream. Okay, it's expressed in cubic feet per second. Okay, and also the channel roughness. If you have a very smooth channel, like a lot of clay, sediment, like smoothing out the bottom of the channel, you'll have faster flowing water. If you've got like jagged rocks at the channel of the river bed, then that's going to kind of frictionally slow down the water. So here are examples of a wide stream. Wide stream, you typically have, or a wide channel, typically have slower moving water, and the reason is because more of that water is coming into contact with the channel bed. Okay, so that provides a lot of friction for the water and slows it down. If you have a more narrow channel, that means the surface area touching the channel is smaller, so less water is being slowed down by friction from the channel bed, so a lot of the water will have really fast velocities at the center of a narrow channel. All right, other factors that affect flow velocity, discharge. When discharge increases, so when rivers swell up with more water, the width, the depth, and the flow velocity all increase. Okay, so if there's more water flowing through a river, you're going to have faster velocity, higher river stage or river level. It's going to be deeper, obviously. And so this kind of information is important. We have an entire governmental agency that collects this information. It's the USGS, or U.S. Geological Survey. They measure flow velocity, discharge, and the river level, the height of the river stage, in more than 7,500 stream gauging stations across the United States. And they use this data for resource management, water management. It's very helpful because if there's ever, a storm, incoming rain event, or a hurricane that dumps a lot of water in areas, the USGS will be able to kind of predict which areas may experience flooding as a result of the water that's coming downriver. Okay, so it's really important so you can warn people that live in floodplains or people that live in areas that may flood often of incoming danger, and that's very helpful for saving lives and saving property, so people can be prepared for incoming floodwaters. Hurricane Florence, I don't know if you remember this, but a few years back hit the Carolinas. So the Carolinas the coastal Carolina dealt with hurricane force winds and storm surge and flooding and stuff like that. But that thing went into kind of like the Blue Ridge Mountain area and just rained like 26 inches of rain in a few days. And it took about 8 days after that for all that water to come through the rivers and back into coastal Carolina. And so not only did people in coastal Carolina have to deal with the hurricane, but then they had to deal with flooding 8 days later. But at least they were warned about it. So here is a picture of all the over 7,000 gauging stations around the U.S. All right, and then this is the cable towers with the cable car, and they usually have wells to measure the river stage. All right, the profile of a river is essentially looking at a cross-sectional view of it. Again, it's like, say you have a cake and you cut the cake out and pull out a piece and look at the distinctive layers in it. This is kind of like the side view of a river, okay? So from the head or the source, the headwaters, to the mouth of the river, you typically have a smooth profile. Gradient decreases as you approach from the head to the mouth. And there are a bunch of factors that change in the different sections of a river. Velocity and discharge are two of those. Okay, so here is an example of a profile of the Kings River in California. The head is over here, kind of in the Sierra Nevada mountains. And then this river kind of cuts through and then makes it out to the Central Valley here. And you can see here the gradient kind of decreases as you approach the Central Valley and then flattens out as you approach the mouth. So here are the factors that change, okay? When you're at the headwaters, the channel slope is really high. The flow velocity kind of starts off pretty high because of that. The channel roughness is really high, right? Because you have exposed bedrock. But as you approach the mouth, so if you go in this direction, so if you're coming down from the headwaters towards the mouth, what happens is discharge increases. So the volume of water slowly increases as you get closer and closer to the mouth. The channel size also increases. Typically in the headwaters, you have narrow channels up here, narrow channels, fast moving water. When you approach the mouth of the river gets wider and wider. And then the flow velocity kind of increases and then settles out as you approach the mouth. All right, so running water does a lot of work on the surface of the earth. It erodes a lot of the existing sediment that's deposited from mass wasting and weathering in the surrounding areas. And it moves, it's like a conveyor belt, moving sediment to different areas on Earth's landscape. And there's three ways that it does it. One is through the dissolve load. This is the invisible dissolved solids that are in water. I'm sure you've been to the ocean and accidentally tasted seawater. It's disgusting. It's salty, right? The reason why it's salty is because it has a lot of dissolved solids in it. Now, river water also has dissolved solids in it, but not as much, so it's still, considered fresh water. But you can have calcium in it, silica, all kinds of dissolved solids that are in river water, and that's part of the sediment load that it's carrying. We call that the dissolve load. Then there's the suspended load. The suspended load are really small particles, silt and clay sediment, really light stuff that remains in suspension. That's kind of like it floats around in the river water and is carried by that river to new locations. And then there's the bed load. The bed load is material that's kind of bouncing on the bottom of the channel, and it kind of continually moves in this direction by sliding and rolling. So the dissolved load is mostly delivered to a river via the groundwater. And the dissolved load's not affected by stream velocity. You can have the fastest moving stream or the slowest moving stream. It has no effect on what the concentration of the dissolved load in the water is. The only thing that can change that is if you have a lot of water evaporating away. So say that river's running through some really dry areas. If the water's evaporating away, it's pure water that's going into the vapor phase. So what's left behind, the river water will be proportionally more concentrated with those dissolved solids because you're removing pure water from it. Then sometimes you can have organisms kind of create hard parts or, like armor around their bodies They typically use calcium. Sometimes some of them use silica, so they'll remove some of the dissolved load out of the river. So that's a biological process. Then there's the suspended load. This is the largest part of the stream's load. It carries the most sediment in suspension. It's typically fine sand, silt, and clay. They're carried in this way. See, if you see this GIF, you can kind of see cloudy water moving through. That cloudiness that's the sediment that's in suspension. During flood stages, typically in the spring, large particles can be carried in suspension. So you can have gravel being moved in suspension with fast-moving river water. And the suspended load is dependent on velocity. The faster stream velocity, then the larger sediment the river can carry. And that's because each particle has a settling velocity, and that's the speed at which the particle falls through a liquid. Okay, so here's a graph. Look at this river over here. You can tell its water is kind of a light brown murky color. That means it's carrying a lot of silt and clay in suspension. So the sediment load in this river is very high. And so here's a graph showing you particle size on the x-axis and on the y-axis stream flow. Okay, so this is in terms of velocity. So say you have water moving at 100 centimeters per second. So that's a meter per second. That would plot right here. So if we draw a line straight down, that means any particle from this size down here, so all clay, silt, sand, and some coarse material will remain in suspension as long as the water is traveling at 100 centimeters per second. Okay. As soon as the water velocity drops, however, say it drops to 10 centimeters per second, so that's roughly right around here. So if we draw a straight line down, now all the coarse material has deposited out because the velocity is too slow to hold that material. So now the only things that remain in suspension are sand, clay, and silt. And that's water moving at a velocity of 10 centimeters per second. All right, and let's say the water velocity drops now to 1 centimeter per second. Kind of slow, right? So go over here and go to that intersection, draw a straight line downwards. And now most of the sand has deposited out because its settling velocity is too fast to keep it in suspension. So the only things that remain in suspension are essentially very fine sand, silt, and clay. Okay, so the take-home message is as water velocity decreases, what you get is the deposition of sediment. And then finally, the bed load of a river. If you look at this image closely, do you see these kind of gravel pieces kind of moving down on top of kind of the sediment of the river channel here? That's the bed load. This is coarse sands and gravel. They move along the bed by saltation, skipping or jumping. You can kind of see it here. They're kind of skipping down. These are the larger particles, so they slide around and roll. So this is more of a localized transport. So moving these larger pieces within the riverbed, kind of downriver a little bit. You know, like if the water's in suspension, that sediment can make it all the way out to the oceans. Here, this is more localized. And during boulders can be moved during exceptional floods by this method. And the bed load can also create interesting features. Potholes that are created essentially with swirling water. You have swirling bed load kind of scouring the bedrock in a river channel, and it kind of create these circular holes, little cold water jacuzzis you can jump into. So the transportation of sediment, there are two terms that refer to the maximum particle size and the amount of sediment a river can carry. Competence means a river that is competent is one that can carry really large particles. And that typically is related to velocity. So if we look at this river here, these are kind of rapids. This water is moving very quickly. So the velocity is very high, meaning that it probably keeps larger size sediment in suspension here. Okay. over on this side, this is a slower moving river. Okay, this is the Mississippi River. If you notice, it's the Mississippi, lower elevation, closer to the ocean. It's a very wide river. You see that its discharge is really high. It's got a lot of water. And so even though the Mississippi is not a very competent river, we would say, carrying large sediment, its capacity is unbelievable, meaning its maximum load. It can carry a lot of sediment. It's a giant conveyor belt moving sediment from the Midwest all the way out to the Gulf of Mexico. And so the capacity is really related to discharge. And if you've ever been to the Mississippi, it's a lot of water moving through. So running water also deposits a lot of sediment and creates a lot of features on Earth's landscape. So deposition occurs when the stream's velocity is less than the settling velocity, and so sediment kind of just falls out of the water. And the largest particles will settle out first, and then the smaller particles kind of slowly settle out after that once the velocity drops. And any deposited sediment left by streams is called alluvium. And you can kind of see that here. Here's a ephemeral stream. It's kind of dried out, and this is all the alluvium that's left behind. So there are a number of features that are produced by deposition. One is deltas, typically at the mouth of the river. This is one that's pictured here. This is the major water body it kind of runs into. And so it leaves a huge complex wedge of sediment with a bunch of distributaries kind of cutting through it, cutting through this area of just unconsolidated sediment. On the edges of a river channel, there are levees or natural levees. They form parallel to the stream channel. And then in floodplain areas behind the levees, you can find swamps or yazoo tributaries. All right, deltas form when sediment in the river runs into a bigger body of water. We call that a base level, or the ultimate base level, which is typically the ocean. Sometimes they can run into reservoirs. So what happens when river water runs into the ocean, the forward velocity of the stream slows down, and so what that does is it lowers its carrying capacity and then deposits a lot of sediment. And what that's going to do is create these depositional landforms, or deltas. Here are some satellite images going through the years on how deltas that are part of the Mississippi River grow over time with more and more sediment building up into the ocean. And this is how deltas form. Okay, so as a river approaches, it hits that ocean, then it dumps its sediment load, and so you see all this sediment kind of piling up into these layers, layer upon layer upon layer of sediment, essentially just stuff that's weathered, transported from the Midwest out into the Gulf of Mexico. But here's the progression, right? So when a river first hits the ocean, it starts depositing sediment, but then it starts depositing so much sediment that it kind of cuts itself off, chokes itself, so the river has to find a new pathway into the ocean. Here it starts depositing a lot of sediment, chokes itself, finds a new pathway, opens up a new pathway, and then you get a complex array of streams and distributaries and rivers kind of dumping out into different areas of the delta. And so this landscape evolves over time and changes. So the Mississippi River Delta is our biggest river delta. And the present delta is called the Birdfoot Delta. We've kind of highly channelized the Mississippi, and now it's dumping out into kind of a further away delta. We call it the Birdfoot Delta because it kind of looks like a crow's foot and just kind of sticking out. But the Mississippi River Delta is a series of coalescing deltas, okay? And I'll show you that over the past 5,000 years, the Mississippi's kind of been evolving and kind of moving into different areas, okay? So let's take a look at that. So here are the historical deltas here. If you think about it, Louisiana is essentially just a river delta, like the entire state. Look at this. Half of the state is just unconsolidated sediment delivered by the Mississippi River. But here are the former locations. Oh, I'm trying to erase this. former locations of the Mississippi River Delta. Here it is, number 1, right? Then it kind of jumped over here. This was the river delta here. Then here's 3. Then all the way out here was the 4th delta. Then the 5th, 6th, and today here's the 7th. This is the Burnsfoot Delta. You can see that satellite image here. And so all of this is just unconsolidated sediment delivered by the Mississippi River. So New Orleans is built on unconsolidated sediment. And what happens with unconsolidated sediment is that it starts to sink as it settles. And that's why lots of areas in Louisiana are susceptible to sea level rise, because not only is sea level rising, but there is a lot of land subsidence here. If you notice, the first delta here is this whole area looks like there used to be a lot of sediment here, but it's slowly kind of settling and sinking away. Now it's giving way to the ocean right here. All right, another depositional landform created by rivers are natural levees. These are raised areas next to the channel, and they form during flood events. So when you have a flood event, that'll flood like flat-lying area surrounding the river and deposit the largest sediments on the edge of the river or the edge of the channel. Okay, and then the finer stuff is kind of laid down on the valley floor. Okay, so after a flood event, the levees prevent water from returning into the river because it's kind of built up, and then you get these swamps and Yazoo tributaries. Okay, so here's a floodplain, flat-lying area. Here's a meandering kind of river moving through it. So during flood stages, this is what happens. Okay, gets completely flooded out, and you see here, here's the river channel, cross-section of it. The coarse sediments are dumped really close to the river channel. Okay, and then you build up those natural levees. And natural levees help prevent flooding in the future. So it's a really weird kind of nature's catch-22, where they're like, well, if you want to prevent future flooding, how about flooding now? And the more you flood now, the more it'll build up natural levees, so the less you flood in the future. So it's kind of weird. But over time, natural levees will build up higher and higher as you have more and more flood events. Another depositional landform that typically forms in drier mountainous areas, the interior of the continents, are called alluvial fans. They're fan-shaped deposits of sediment as kind of ephemeral rivers, or rivers that only form in a portion of the year. They don't run year-long. All that water kind of runs down a mountain front and then dumps out into a low-lying valley floor and just pukes out all this sediment. Okay, it's mostly sand and gravel material. I'll show you a picture. But here's an example in Death Valley. So all the sediment just kind of is deposited out in this wedge, kind of fan-shaped deposit. So that's an alluvial fan. All right, let's talk about the different stream channels. Bedrock channels are channels that cut directly into the underlying bedrock. Okay, they form in the headwater regions, so at high elevations, right, where you have exposed rocks. Here's a picture of a bedrock channel. All right, typically what you see here, there's a steep slope, high gradient. That means you have energetic flow of the water, rapids. You'll typically see steps and pools, waterfalls, rapids, that kind of stuff. Alluvial channels, on the other hand, are channels that form when you have sediment that has previously deposited in a low-lying kind of valley area. And that's associated with the floodplain, kind of a broad, flat area where you have a river kind of slowly meandering through a flat-lying area. Okay. The channels can change in shape as the river kind of evolves through time and erodes in some areas and deposits in other areas. And so the patterns in the channel really reflect the stream's ability to kind of transport sediment around the areas. And so there's a few types of alluvial channels. One such is a meandering channel. This is where kind of a stream meanders back and forth. I want you to visualize being at an airport and you're going through that airport security line where it kind of goes back and forth before you get to the TSA agent. that's a meandering line, or like lines at Disney meander back and forth before you can get on the was it Flight of the Passage. 2-hour wait. It was totally worth it. So essentially, these are deep, smooth channels that primarily transport silt and clay. And the cool thing is they evolve over time. They change because these meanders they grow larger and larger, and then they form a cutoff, meaning like they erode in certain areas, and the meander loops get so long that they end up cutting each other off, and then you leave behind what you call an oxbow lake. All right, a cut-off oxbow lake. And then that dries up, becomes a swamp, and then dries up together. But then the meanders start to grow and migrate again, because in this type of meandering river, you have cut banks, and point bars. Cut banks are areas where there's active erosion, and on the inside of a meander, you have a point bar where there's deposition. Let's just go to the picture. It's easier to visualize here. So here's a meandering river. Look, back and forth movement of a river. Okay, and so what happens in a meandering river is the water velocities within the river is not the same. Okay, the fastest velocities are on these kind of turns here. We call those cut banks. We have faster flowing water, maximum velocity, then you'll have a lot of erosion. And if you happen to build your house on a cut bank, bye-bye, because that's going to erode away the foundation of your house, and you're going right into the river. Okay, so this area, it's kind of like the edge of the meander here. This is called a cut bank over here. And as they evolve over time, they kind of move in this direction. So they make the meanders kind of longer and longer, okay? Just opposite of the cut banks, you'll find these areas of sand that is deposited. Those are called point bars. And then this is where you have the slowest velocity of water. And so if you have slow moving water, then you'll have deposition. And so sometimes, I don't know if you've seen some of these or walked along a meandering river, but these are those like sand banks that form. Okay, so over time, how they evolve essentially is, see this huge meander loop, right? So if you're riding this river, you'd be like, what the heck? I was just there. What's going on? Right? But what happens is over time, these cut banks can join together. So there's a cut bank here and a cut bank here. And then as those continually erode, you'll create a cutoff, right? And now the river kind of is straighter and leaves behind a huge meandering loop called an oxbow lake. So if you think about it, these meandering rivers evolve by like widening and then narrowing and then widening and narrowing for thousands of years. They'll continually do that. And that's how these meandering rivers evolve. Another type of alluvial channel is called a braided channel. A braided channel is kind of like a complex network of converging and diverging channels, and typically they move through these kind of piles of sediment or gravel bars. Though that sediment is typically left there, typically in the interior of continents where perhaps there are mountains close by. The reason why that sediment's all there is a lot of times it's because of ancient glaciers, that kind of continental glaciers that just scoured the landscape and left behind these huge moraines of sediment. And then now that we're in the interglacial period, we have rivers kind of moving through that area instead of glaciers. And then as those rivers kind of move through those giant pile or moraines of sediment, they'll cut through it like in this braided fashion. Okay. So here's a better view of it. See, it's kind of like braided hair, a river kind of cutting through all these island gravel bars. So that's a braided stream. Okay, so the base level, that's a term used to describe the lowest point a stream can erode to. And so there's two types. There's the ultimate base level, which is the ocean, and there's a temporary base level, which could be like a lake or a reservoir. We can dam up a river and create a reservoir. That would be a local base level. And so what happens is the characteristics of a river can change if if a base level is readjusted. Okay, so for example, there can be some natural readjustment. Let's pretend there's a fault and an earthquake, and this whole land area is lifted upwards. Okay, so here's the typical profile of a stream. All right, down here, this is the meandering part of the stream, very close to the base level. Here's the mouth of the river, and then this is the kind of higher areas. All right, so up here you'll have the river kind of down cutting, right, and it'll be like a more narrow river, V-shaped valley. Then as you approach the ultimate base level here, then you'll have a meandering river where the erosion is focused side to side. But if there's any change in the local base level, this whole area will raise up and you'll create a waterfall, and then now the river is focused on cutting downward to get to its local base level. So over time, as a river evolves, it will evolve to try to get to its ultimate base level, which is the ocean. And so an evolved floodplain or valley will have a meandering stream here. So that leads us to understanding how rivers kind of shape or cut the landscape that they're in. And they typically form two types of stream valleys. They form wide stream valleys or narrow stream valleys. And so the valleys are shaped by weathering, the flow of the water, and mass wasting. And narrow valleys are V-shaped. So you can see that picture here. See that? That's a V-shape. This is typically up in the mountains, higher gradient, far away from the ultimate base level. And because you're far away from the base level, the river focuses on down cutting, right? So water wants to get to the lowest possible point, and if you're really far away from that, high up in the mountains, it's going to erode downwards, and what that creates is that V-shaped valley. All right, and so characteristics of those narrow valleys, they often include rapids, waterfalls. You can see that pictured here. Okay, faster flowing water, bedrock exposed bedrock channels, steps and pools. Wide valleys, on the other hand, that is a river that's closer to the base level. So because the water is closer to the base level, it no longer needs to kind of erode down to the base level. It can focus its erosion in a side-to-side fashion, like that meandering river we've been talking about. So downward erosion is less dominant. The stream energy is focused side to side. All right, here's another example of a V-shaped valley. This is in Yellowstone National Park. Here's the Yellowstone River. So there's a waterfall, fast-moving water. This is at an elevation of about 11,000 feet, so very far away from the base level of the ocean. So downcutting is very important here. And then here's the development of a wide stream valley. Okay, so over time, the older a stream gets or more evolved it gets, you'll have a well-developed floodplain. So you initially start off with a V-shaped valley, so the river kind of tries to cut down to its base level, and as it does, once it reaches the base level, then it focuses its erosion side to side. And remember how those meanders kind of evolve. They go really wide and narrow, wide and narrow. Well, that action kind of widens the floodplain valley over time. So as a river evolves, going from far away from its base level to closer to its base level, it creates a very flat floodplain that you can see here. Okay, so the characteristics of wide valleys is that you have a well-developed floodplain. You'll have meanders, cutoffs, oxbow lakes. You can see that process in that image here, the formation of an oxbow lake, meandering loops that grow larger and larger, then cut off and become more narrow. That's typical of a wide valley. In some rare cases, you can have a river like what we see here, the Colorado River. It actually used to be close to its base level about 20 million years ago, but then uplift started to happen, and the entire Colorado Plateau was lifted from sea level to about, in the lowest lying area, 6,000 feet to where it is today. And what happens is that river kept its meandering style. So it was meandering because it was very close to the ocean. So as it was uplifted, downcutting became more prominent, but it kept its meandering shape, and then you're left with what we call an incised meander. So it's a beautiful landscape here. You can see this river kind of meandering back and forth, despite the fact that it's not evolving like a normal meandering river because it's far away from its base level. So floods are part of living by river channels. They're the most common geologic hazard. They cause the most property damage. And what causes floods really is crazy weather, low pressure systems, hurricanes, storms, and also just regular, the time when floods occur most is in the spring. So once snowpack begins to melt, then that starts kind of moving through the headwaters and into lower lying areas like floodplains, where you would see more water build up and more discharge, and that's where you would see a lot of flooding. But human interference can mess with the stream system and actually exacerbate the problem. We can have larger floods as a result of our actions. Here's an example of a Mississippi River flood. Okay, satellite images from 1991. Okay, here's the normal kind of Mississippi River, Illinois River kind of meeting together. And then during a flood stage, you can see these swell and almost quadruple in size. Now keep in mind, here's the scale, right? So from here to here is about 10 miles. Okay, so this swells to about, I mean, if I'm eyeballing it, but this is about 5 miles. So if you lived within 5 miles of the Mississippi River, your house would be underwater. Or at least water will be coming into your living room, right? You get the black mold. All right, another problem you might deal with are flash floods. Here's a desert flash flood. Pretty scary. It doesn't even look like water. It's just a lot of sediment laden in the water. But they can be pretty dangerous. They occur with little to no warning. A lot of times this happens in desert areas because they don't have a lot of water. So when there is a rain event, all that water kind of funnels and channels into dry riverbeds, and you have a kind of flash of water moving through an area. Mountainous areas are particularly susceptible to flash floods because when you live in areas of steep gradient, it'll kind of channelize the water into certain smaller areas, and then you'll have water moving quickly through those areas. One example is in Zion National Park. The Narrows is an area you can walk through. It's kind of like a little river that you can wade through as part of the national park, like trails that you can go on. And that place, if it happens to rain there, all the water gets channeled into those areas, and the water level can rise like 15 feet in a matter of minutes, which is pretty scary, and people have drowned as a result of it. In 2011, there was a flash flood in New York and Vermont as a result of Hurricane Irene. And look at this damage. Right? Imagine if I-4 sustained damage like this. How many decades it'd take them to fix that? It'd be ridiculous. But here's an example. Look at this. Flash flood caused all this damage to this road. Nearly 2,000 damaged road segments, 300 damaged bridges, and 800 damaged homes as a result of this flash flood. Here's the data from one of the local rivers. Typically, it's flood stage, or the level of the river is 4 feet, so you could kind of like wade in that water if you wanted to. But during the flood event, look how high that got. It got almost up to 18 feet. That's an increase, 18 feet. So you'd be completely inundated. That topped the levees of the river and then started just flooding surrounding areas. So there are a lot of ways to control or flood control measures. A lot of engineering efforts. Here in Florida, you'll see them a lot. Artificial levees or flood control dams. We create canals and channelize water out into the ocean so that there's less flooding inland. We do that a lot here. A lot of water management here in Florida, or you build dams like the dam along the south side of the Okeechobee, Lake Okeechobee. But here in Florida, we have a lot of kind of agricultural canals that we've constructed, and that essentially, and they're often kind of taken care of and channelized and dug deeper so that it forces the water to go out into the ocean and then drains the local land area. And then you'll see those flood control dams every once in a while. Sometimes they close them during times of when it's really dry to hold more water inland. And other times, if it's raining too much or if we have a hurricane, they'll open up those flood control dams and let water kind of go out into the ocean so that we could kind of sustain more water during rainy periods. But really, in terms of floodplains, when you live near a floodplain, The non-structural approach is the best, letting these areas flood because they're going to flood anyways, and allowing the sediment to kind of deposit in those areas. I mean, we shouldn't really be living that close to rivers in floodplains because we're just going to constantly be dealing with property loss.